Good afternoon. This is our very short video lesson for metamorphic rocks. We're going to be able to squeeze all this into one lesson. So you will be watching the narrated PowerPoint for metamorphic rocks, of course. And I speak about all these things in the narrated PowerPoint, but our notes on the board here are just to emphasize the most important things from metamorphic rocks. And you really need to watch this video because we are going to do precious little of this, if any, in class before our exam. Metamorphic rocks are just not all that important. Okay, so what we're looking at here are just some common metamorphic rocks and the parent rock they come from. Well, you need to know this for your exam. Yes, you will. It will be in the form of matching. So quartzite, the parent rock is quartz sandstone. Makes sense. Marble will fizz in dilute hydrochloric acid. That kind of makes sense because its parent rock is limestone that also fizzes in dilute hydrochloric acid. Now slate, its parent rock is always shale. You're going to see that shale can be more than one parent rock. Then we have something called gneiss. The G is silent. Gneiss. Gneiss can have one of at least a couple different parent rocks. It could either be shale or granite. All right, now we're moving to another part of the board. Okay, so now we are looking at the agents of metamorphism. In other words, what are the particular things that are working on that rock and changing it? Remember that metamorphism is going to occur without melt. So rocks are going to change due to mainly heat and pressure, but they're never going to melt. If they melted, they would be an igneous rock. So this is part of the rock cycle that you learned, way back, maybe going to grade school, I would guess. So the four agents of metamorphism are heat, and that heat could just simply be the geothermal gradient, which we discussed back in igneous rocks, or it could be that you have an igneous intrusion nearby, and that is giving you enough heat to metamorphose the rock. Pressure is involved. Not only do you have increasing heat with depth, but you have increasing pressure with depth. Hydrothermal fluids, that just refers to heated groundwater. And these are especially common if you have active volcanoes in the area. Magma chambers heating up that groundwater. So circulating hydrothermal fluids may or may not be present. Hydrothermal fluids, by the way, play a large role in changing limestone into marble. And then the fourth agent of metamorphism is something called differential stress. And as you will learn in the narrated PowerPoint, differential stress just refers to the fact that you're going to apply forces to a rock unequally in different directions. So we have two types here. We have normal and shear. By the way, differential stress may or may not be present. So normal shear, so we start there with something that looks pretty much like a cube. And you notice from the length and thickness of the arrows that we're squeezing greater in an up and down direction than in a side to side direction. Okay, so what's important here is that we're applying differential stress. We're going to apply compression greater in one direction than another, and we're going to apply those forces perpendicular to the rock. Or we could think of it as applying them perpendicular to a particular mineral, like a feldspar crystal. So what do you end up with? You end up with that image on the right, which looks more like a rectangle. So you have elongated this feldspar grain because you applied normal stress. The second type of differential stress is called shear stress. And in this case, we're going to apply a force, like squeezing, greater in one direction than another. So we're applying that force to the top and bottom of that rectangular feldspar crystal and not much on the sides. But this time we're going to apply the forces parallel. So look at the arrows there on the top and the bottom. The forces are being applied to this mineral crystal parallel and going in opposite directions. So what is your shape change? What do you end up with? You end up with that image there on the bottom right, which is a rhombohedron. Okay, now we're going to move over here and we are going to discuss recrystallization versus neocrystallization. So what happens to individual mineral crystals during metamorphism? Well, more than just these two things, but these are the only two we need to worry about at this level of the course. So either recrystallization or neocrystallization. So recrystallization refers to the size, shape, and arrangement or orientation of mineral crystals, grains, changing. So you change the size, shape, or arrangement of the minerals, but you do not grow any new minerals and you do not destroy any new minerals. So I have an example drawn there for recrystallization. You see two circles. The circles are representing looking down into a microscope at thin slices of rocks. We're comparing two rocks here. On the left, you're comparing quartz sandstone. On the right, you're comparing quartzite. So the quartz sandstone on the left, this is what your thin sliver of rock would look like under the microscope. So this was a beach sandstone. So it's well sorted, well rounded, quartz sand, and there's a lot of open space, a lot of porosity and then permeability as well. On the right, that's the metamorphosed version of sandstone. It's called quartzite. So it's still quartz. You began with quartz and now you end with quartz. But look at the drawing. It's very different. So instead of having rounded, well-sorted quartz sand grains, you have these interlocking quartz crystals. So the size has changed, the shape has changed dramatically, and the arrangement has changed. You now don't have any porosity or permeability. You just have interlocking quartz crystals. Examples of metamorphic rocks that have experienced recrystallization are quartzite and marble. All right, so then down there at the bottom, neocrystallization. That's the other thing that will happen, that could happen to the minerals in our metamorphic rocks. So neocrystallization basically just says that you are going to grow new minerals at the expense of old minerals. So old original minerals are destroyed in the process of changing those minerals into something else. That's why it's called neocrystallization, new. So I can't really draw how that happens. It's a very slow process under heat and pressure and differential stress. We will simply give an example. You begin with shale, a common sedimentary rock. That's just a bunch of clay minerals. What do you end up with? Under a medium to high grade metamorphic event, you end up with a completely different rock called garnet mica schist, which is a real pretty rock. I like to pass this one around in class, but we're not going to do that in the age of COVID or in a summertime when we have fully online classes. All right, moving over again, we are going to now take a look at foliation. What is foliation? Foliation is a preferred alignment or arrangement of minerals. Okay, some rocks, some metamorphic rocks are foliated, some are non-foliated, so they don't all have this. Okay, so the only way you get foliation is that it's going to form in the presence of differential stress. So of our four factors of metamorphism, the one that must be present to form foliation is differential stress. That's an exam question. Well, everything up here on the board is an exam question. What might foliation look like? It might look like parallel micas. Okay, so examples of foliated rock include slate. In the case of slate, you don't necessarily see minerals unless you do have some mica crystals growing and you might see a little sparkle and shine. But garnet mica schist is a great example of a foliated metamorphic rock. It's basically a bunch of parallel micas that you can easily see in the hand sample, and you may or may not have garnets there. And then there's gneiss again with the silent G, also referred to as banded gneiss. That is an example of a foliated metamorphic rock, of course. And then examples of non-foliated metamorphic rocks would be quartzite and marble. And what does that mean? It just means that there is no preferred mineral alignment. It's still a metamorphic rock. Quartzite and marble are both metamorphic rocks, but there's no alignment of minerals. It's just interlocking crystals of either quartz or calcite. So those are non-foliated. All right, we are briefly going to discuss low-grade metamorphism versus high-grade metamorphism. So how much heat do you have? How much pressure? We can have low-grade metamorphism. We can have intermediate grade metamorphism, which I don't have on the board. We could have high grade metamorphism. We don't need to spend much time on metamorphic rocks, period. So low grade metamorphism, this will be a little bit of heat and a little bit of pressure. Our best example here is shale turning into slate. They actually look very similar to each other, but slate is a stronger rock. And in that case, you've lost some of the clay minerals and are now growing a mineral called chlorite. Now the chlorite crystals are generally too small to see with the naked eye. Again, we're skipping intermediate. High grade metamorphic rock. I might want you to know an example of a high grade metamorphic rock. Shale can turn into something called banded gneiss. So in the case of high grade metamorphism, you have high heat and high pressure. So if shale turns into either garnet mica schist or gneiss, that means that that was a high grade metamorphic event. So high grade metamorphic events are more likely to occur, say, deeper within the mountain root, buried to a deeper depth, while our low grade metamorphic events can occur in the relatively shallow subsurface. All right, we're now going to move to a different board and finish up this quick video lesson on metamorphic rocks. Okay, there's some light glare, but I do know from uploading the last video to YouTube that the light glare doesn't look as bad on the video as it does here in the room. Not a lot we can do about that. I've tried arranging the lights in different ways. There's just too much sunshine outside. Okay, so contact metamorphism versus regional metamorphism. Contact metamorphism, this is small scale, more localized, and it's metamorphism as a result of an igneous intrusion nearby. So you have the right plate boundary to produce magma and produce active volcanoes. You've got an igneous intrusion, magma chamber, very hot material, 1600 degrees Celsius, that also can lead to some hydrothermal fluids, and you can get metamorphism of the rock surrounding the magma chamber, creating something we call contact metamorphism. You can see more about that on the narrated PowerPoint. And then regional metamorphism, this is on a much larger scale. Okay, this is a result of mountain building at convergent boundaries. We'll talk about plate boundaries after we get finished with the second exam. So, regional metamorphism by far produces the greatest volume of metamorphic rock on this planet. And if we were to look at, just even think about mountain ranges, the Himalayas, the Appalachians, the Rocky Mountains, the Sierra Nevada Mountains out west, the Andes Mountains in South America, there are just tons of metamorphic rock deep within that mountain range. Sometimes the metamorphic rock does make its way to the surface. How does that happen? I'm going to leave that for you guys to read about, listen to when you watch the narrative PowerPoint, where we will talk about, in addition to the things I've filmed here today, we will discuss shock metamorphism, and we will discuss how you can bring metamorphic rock to the surface, a process we refer to as exhumation. Okay guys, that's it. This is a very short lesson, and I'm glad because it's been a long day already.